In this session, we're going to take a look at random variables. A random variable is a function that assigns a real number to each element of the sample space. So a random variable x will map the sample space to the real numbers. Okay, random variables are usually denoted by capital letters like X, Y, and Z, and the values that they take are written as corresponding lowercase letters, small x, small y, small z. So as an example, the experiment is to roll a die once. The sample space then consists of the results 1, 2, 3, 4, 5, 6. And we can have a random variable y. We define it this way. It takes the value y equals 1 if the die shows an even number, and it takes the value y equals -1 if the die shows an odd number. Okay, so now y, the value of y depends upon a random experiment, so y itself is random, and we can assign probabilities to y. So the probability that y is equal to 1 is the probability, how did y take the value 1? The roll of the die was even. So what's the probability of getting an even roll of the die? That's 1/2, 3 out of 6. Right, what's the probability that y is equal to -1? Well, in order for y to be equal to -1, we must have had that the die gave an odd result. And the probability of getting an odd result is 1/2 for a fair die. Okay. And we would use notation like this. So the probability that y takes a small value, takes the value small y, is 1/2 for small y equal to +1, and it's equal to 1/2 for small y equals -1, and it's equal to 0 otherwise. Okay, let's take another example. Let's say we have a fair die, and we roll it 100 times, and we record the results of each roll. Okay, the sample space for this is this has 6 to the 100 elements, right? It'd be easier to work with a random variable than to work with the sample space. We are interested in how many times a 6 occurs. So let x be the number of times that a 6 occurs. Okay, so the notation p of x is equal to 20 would mean the probability that a 6 occurs 20 times. So it means that, okay, p of x equals 20 means the probability that 6 occurs 20 times. P of x is equal to small x means that what's the probability that the random variable x takes the value small x. All right, another example. So that's an example of a discrete random variable. An example of a continuous random variable is the following. You have a velocity of a molecule in a gas. So you measure the velocity of one molecule in a gas. The sample space is an infinite set of vectors, and they lie in a continuum, right? Their components could be any real number. And we define a random variable as the kinetic energy of the molecule, mv²/2. So that takes values anywhere going from 0, any real number short of infinity. Okay. So in the previous case, the results were discrete. The values that the random variables can take are discrete. Here, the values that the random variable can take are continuous. Okay, so we make this distinction between discrete and continuous random variables. Discrete random variables take discrete values, and continuous random variables take values in a continuum on an interval. Right. Now, recall that for y, we worked out the probability that y takes particular values, +1 or -1. Okay, so we basically worked out what's called the probability mass function for y. Okay, so we want to have a definition for probability mass functions for discrete random variables. Okay, that's basically the probability that the discrete random variable takes certain values. What's the probability of it taking this value or that value? That's told to you via the probability mass function, or we call it short form PMF. Okay, so here's an example. We have a 6-sided die. We're going to roll it once. The value takes the random variable x takes a value 1 if the roll gives a 6, and it takes a value -1 if the roll gives anything else. So the PMF would tell us what the probability that x equals 1 is, what the probability that x equals -1 is, and what the probability that, say, x equals 0 is. Okay, what's the probability that x is equal to 1? Well, for x is equal to 1, it takes value 1 if the roll gives a 6. So the probability that the roll gives a 6, well, that probability is 1 out of 6. And the probability that x is equal to -1 is if the roll gives anything else. So you have a 5/6 probability of getting anything else but a 6. But the probability that x is equal to 0, well, the random variable x never takes the value 0. So the probability that the random variable x is equal to 0 is 0. The probability that x takes any value other than -1 or +1 is 0. Okay, so the probability mass function definition. So you have a discrete random variable, capital X. It's, I'll try to be consistent in my notation. The PMF for that will be written as small f sub x. And so this probability mass function of the discrete random variable has these properties. The values that it takes should be greater than or equal to 0. The sum of all of these values should be equal to 1. Right? The sum of all the probabilities should be equal to 1. And the probability that x is equal to small x is given by the value of the PMF at small x. Okay. So continuing with the die example, the variable capital X takes the value 1 if the roll gives a 6, takes a -1 if the roll gives anything else. What would be the probability mass function for this? Well, f sub x is equal, the f sub x of 1, sorry, f sub x of 1, f sub x of 2, x sub x of 3, 4, 5, those are all equal to 5 out of 6. Sorry, I've got that wrong. X only takes values 1 and -1. So f sub x of 1 is equal to 1, is equal to 1 over 6. And f sub x of -1 is equal to 5 over 6. And f sub x of x is equal to 0 whenever x is not equal to 1 or -1. Okay, so that would define the PMF for x. Okay, cumulative distributions are related to the probability mass function. Okay, here's an example. we don't ask what's the probability that x is equal to 4. We're asking what's the probability that x is less than or equal to 4. So x, the value of x comes from rolling a die, right? So you roll a die and x takes the value of the roll, the number that comes up. What's the probability that x is less than or equal to 4? Well, that's the probability that x is equal to 1 or 2 or 3 or 4. That's 4 out of 6 is 2/3. Right, so that's an example. Working that out is an example of working out a CDF. Right, so you don't want to know that the probability that the random variable is equal to a particular number. You want the probability that the discrete random variable has a value less than or equal to some number. Okay. So if this, I'm going to try to be consistent in my notation. Small f sub x will mean the PMF, or the probability mass function for f. And the cumulative distribution will be given by capital F. That the notation for that will be the capital F of x. Okay, so the capital F sub x of x is defined to be the probability that the random variable x takes a value less than or equal to x. And that's basically just the sum over all possible values of small x. T, the f sub x of t. Okay, so you roll a die, x can take values depending upon the roll of the die, whatever the result was, x can take values 1, 2, 3, 4, 5, 6. So we want to work out the cumulative distribution, cumulative distribution for x. So we can work out that from the probability distribution, the PMF. The probability mass function. So the probability mass function has small f sub x would give you for values 1, 2, 3, 4, 5, 6, it should give 1/6, and for all other values you get 0. Now you can sum those up in order to get f sub x of various values. Okay. So this is what the probability mass function looks like, f sub x of x. All right. Now, what does the CDF look like? Cumulative distribution. Well, for values less than 1, what is the probability that x takes the value x less than 1? Well, it's 0. It never gives values less than 1. Okay. What about values that lie between 1 and 6? Well, what about, let's take a few examples. If I have the value 1, what's the probability that the random variable x takes the value 1 or values less than 1? Well, the value that it can take is 1. The probability of that is 1 out of 6. Okay, what about 1.5? What's the probability that x takes a value less than or equal to 1.5? Well, out of all those numbers, the only one that it can actually take is 1, and the probability that it takes the value 1 is 1 out of 6. What about 2.3? Well, the values that it can actually take, which are less than or equal to 2.3, are 1 and 2, and the probability that it can take a value 1 or 2 is, well, f sub x of 1, small f sub x of 1 plus small f sub x of 2, which is 1/6 plus 1/6, which is 2/6, and so on. Okay. The probability that x takes a value bigger than 6. Okay. Well, what about, let's try this out. What about 7.3? The probability that x takes a value, well, the only values that it can take are 1, 2, 3, 4, 5, 6. So the probability that it takes a value less than 7.3 is 1. Okay. So we sum up all of that over here, and these brackets here, these L brackets, that they stand for the least integer function. So the least integer of x is the integer closest to x, which is less than or equal to x. So f sub x of 5 is the least integer of 5 over 6. Least integer of 5 is 5 over 6. Okay, now for continuous distributions, and we don't call it a probability mass function, we call it a probability distribution function. It kind of does the same things for us. And we're going to replace sums with integrals. Okay, so the PDF, or the probability distribution function, small f sub x, for the continuous random variable x, that is a probability density function for a continuous random variable x if, one, you need all those probabilities to be greater than or equal to, probability densities to be greater than or equal to 0. The integral from minus infinity to infinity of f sub x of x dx is equal to 1. And the probability that x lies between, on an interval between a and b, is given by integrating from x equals a to x equals b, the integrating the PDF from a to b. Okay, so for example, f sub x of x is equal to lambda e to the negative lambda x when x is greater than or equal to 0 for some positive constant lambda. Otherwise, it's equal to 0, right? On the negative numbers, it takes the 0 value. Okay, so can this be a probability density function? Well, you need that the values it takes are always non-negative. Okay, so for lambda greater than 0, yeah, all the values that it takes are non-negative. And you need that if you integrate this from minus infinity to this alleged PDF, if you integrate that from minus infinity to infinity, you should get 1. Okay, so let's do the integral. The integral from minus infinity to infinity of f sub x of x dx. Okay, so from minus infinity to 0, this all takes value 0. So you don't really need to integrate that. And then from 0 to infinity, it takes the form like lambda e to the negative lambda x. So if you integrate this from minus infinity to plus infinity, lambda e to the negative lambda x dx, well, it turns out that you do indeed get 1. And so this is a candidate for a PDF of some random variable. Okay, cumulative distribution, just like you had cumulative distribution function CDF for, in the discrete case, you have one in the continuous case also. And this is the probability, again, f sub x of x is the probability that the random variable x takes a value which is less than or equal to x. And then from the definition of the probability density function, this is the integral from t equals minus infinity to t equals x, f sub x of t dt. Right? You integrate the PDF from minus infinity to x. Okay, so if we continue with our example, in order to get the CDF from the PDF, we integrate from minus infinity to x, the PDF evaluated at t dt. Okay, but this takes value 0 from minus infinity to 0, so we don't need to worry about those. So now we can integrate from t equals 0 to t equals x, Now, what's the form of the PDF? It's lambda e to the negative lambda t on that interval. Integrate that with respect to t, and you'll get 1 minus exponential of negative lambda x. Okay, well, once again, integrate for x less than 0, the contribution is 0. We're not going to worry about that. Okay, 2 useful results. One is that if you have the CDF, supposing you're asked from the probability that x takes values between a and b, well, you can either integrate the interval from minus, you can integrate the PDF from x equals a to x equals b, and you get that result. But if you happen to have the CDF on hand also, then that is the CDF evaluated at b minus its CDF evaluated at a, and that will also give you the same result. And the CDF was found by integrating from minus infinity to x, right? So if you want to find the PDF from the CDF, then the PDF is at x is the derivative of the CDF at x. Okay. Now we move on to the expectation of a random variable. So expectations and variances help us to characterize random variables. So again, the notation, I have random variable capital X. Its PMF or its PDF will be written as small f sub x. Its CDF will be written as capital F sub x. And what we're interested in right now is the expectation. So that's either written as, sometimes it's written as mu sub x, and sometimes it's written as e of x with square brackets. And these, you read these notations as the expectation of the random variable x. Okay. So as an example, we toss 50 coins, 100 coins into the air. How many heads come up? That's a random variable. And let's say x, we would like to know what the expectation of x would be. How many heads would we expect to see? All right, instinctively we think it should be 50 if these are fair coins. If you get 53 or 52 or 47, you probably wouldn't worry about it. If you get like 87, you might start thinking whether the coins were actually fair or not. Okay, so this is the definition of the expectation. Mu sub x or e of x, the expectation of the random variable x. In the discrete case, when you have the PMF f sub x, you get that by the summation over all values, allowed values for small x times f sub x of x. Okay, so that weighted average is the expectation. And in the continuous case, what you do is if x was a continuous random variable, then mu sub x or e sub x will be given by integrating from x equals minus infinity to x equals positive infinity, x times f sub x of x dx. X times, you integrate x times the PDF from minus infinity to infinity. Okay, so let's do an example of calculating an expectation for some random variable. So we toss a coin twice and we note the results. So the sample space is head, 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 tail, tail, head, tail, tail. And the random variable x is the number of heads. So it can take, here it takes the value 2, here it takes the value 1, and here it takes the value 0. So a capital X, right, the random variable capital X can take values 0, 1, and 2. Okay, so x equals 0 means no heads. That's one case out of 4, one result out of 4 equally likely results. So the PMF takes a value 1/4 for x is equal to 0. For x is equal to 1, one head means, well, that's two outcomes out of 4 equally likely outcomes. So that's it. For x is equal to 1, the PMF should take the value 1/2. And for 2 heads, well, that happens with, that's one outcome out of 4 equally likely outcomes. So that has a probability 1/4. So the PMF should take the value of x, should take the value 1/4 for x is equal to 2. Okay, now from the definition then of the expectation, the summation x times f sub x of x. So that would be 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4. So we calculate the expectation, we get 1. Okay. Let's do an example with a continuous distribution. So let's say that I have a random variable, a continuous random variable, capital X. It has a CDF, capital F sub x, defined by this: f sub x of capital F sub x of x is equal to 1 minus e to the negative x for x greater than or equal to 0. It's 0 otherwise. Okay. Well, if I want to calculate the expectation using the formula that I have, I need to integrate x times the PDF, not the CDF. Well, I can get the CDF from, I can get the PDF from the CDF, small f sub x, from capital F sub x by differentiating. Okay, so if I differentiate 1 minus e to the minus x for x greater than or equal to 0, I get e to the minus x for x greater than or equal to 0. And I differentiate 0 for the negative inputs, and I'll get 0. So this is the PDF, f sub x. It has the form e to the minus x for x greater than or equal to 0 and 0 otherwise. Now I'm going to integrate f sub x of t. Now I'm going to integrate from x equals minus infinity to infinity, x times f sub x dx. And that's the, right, we don't worry about the part that's 0. So that's the same as integrating from 0 to infinity, x e to the minus x dx. And if I do that integration, let's say by parts, then I will get that the expectation is equal to 1. Okay. If you've forgotten integration by parts, you might want to review it because you are going to need it. Other points in this course. Okay, I'll see you next time.